Recording this time. There we go. All right. And we're back. So, uh, briefly, I don't want to spend more than like 5 minutes on this, like that ever happens. I gave you a little paper to write, VMware versus parallels. So, what did we find out? Compare the two of them. Is one better than the other? One better for certain tasks than the other? First of all, they're both for Mac, right? So, VMware has a product called Fusion for the Mac, and they also have a normal VMware product for the PC, and then you have Parallels. So what did we find out? Certainly it's a matter of preference. Is there advantages to one over the other? Does one do certain tasks better than the other, and another one does other tasks better than the other?
Fusion had better IT security stuff.
Okay. So maybe if you're implementing this in an enterprise type situation, VMware might be the choice. Where Parallels maybe makes more sense for consumer. Okay. What about specific applications? Does one have better 3D support than the other? Kind of probably lends itself to this comment we just said. Typically, Parallels really focuses on having consumer things that consumer care about support. Where VMware Fusion is a spin-off product from their normal VMware solution for PC. That's been around for a while. So VMware is kind of the, let's say Microsoft Windows of virtual machines, something like that. But when Parallels comes out, and this kind of goes along the lines of what we were talking about with the evolution of Microsoft operating systems, where you had the NT kernel and you had the 9X kernel, and eventually those two merged, but one was the consumer operating system and one was the business operating system. The business operating system had all sorts of stability features, but lacked a lot of the driver support to play video games and crap like that. So Parallels tries to make the end user experience good for consumers, where VMware, it's not that they don't pay attention to that, but they probably have a affinity for security because they really want their markets to be in enterprise. Not that you can't buy VMware Fusion as a single license at home, but VMware Fusion has VMware has a whole suite of products for delivering virtual machines in mass at the enterprise level. Kind of make sense? Why would a corporation want to host 100 virtual machines? What's the advantage of that? Go ahead.
You don't really have to go out and spend a bunch of cash on hardware.
Okay. You really just need enough hardware. You need a keyboard and a mouse and a network connection to remote into the virtual machine, because we have a virtual machine server, right? And what's the advantage of having a virtual machine rather than a single machine, a single piece of hardware? It actually comes down to more of an IT support type thing. So certainly a cost. There's a cost thing. But now, let's say you have your home-based computer and something goes wrong with it. You take it into Evan at Best Buy. Said, "Hey, fix this," and Evan picks his nose and what's up? Throws it across the room. It's like they was that skit on TV or on YouTube with the Amish IT support. You seen that one? Some company, it's like a joke thing where they call IT and they send, the Amish guy down to fix it. He's like planing the monitor, and then decides it's broken, and it's funny. You should look it up sometime. Not now, but sometime. But in any case, so consumers would take their computer into a computer repair place. Could be Geek Squad at Best Buy or whatever, and say, "Hey, I need this fixed." Well, in an enterprise type situation, that's loss of productivity if you have to have downtime with your computer. Well, with a virtual machine, if they're backing up your personal data on a nightly basis, or especially with cloud computing stuff today, your personal data might be backed up to the second. They can just deploy the last known good copy of your virtual machine in 5 minutes. Something's wrong, I'm not even going to look at it. Wait 5 minutes, it won't be wrong anymore. So that's an advantage. What's the disadvantage of running a complete virtual machine environment? There's got to be downsides. How many of you in here run solely on a virtual machine? None of us, right? Why?
Machine would be slower.
Definitely be slower. Slower for everything? Well, I guess the short answer is probably slower for everything. Noticeably slower for everything is maybe the better question. I would say if you're running Microsoft Word or something like that, human being might not necessarily, as long as you're running something appropriate for running a virtual machine. If you're running on a single core, old laptop, virtual machine is going to be slow. It's going to be slow. But if you're running on one of our, more modern, beefier quad core computers with plenty of RAM, stuff like that, if you're launching a virtual machine and you're trying to run Microsoft Office or something, it'll probably feel like it's running at full speed. I think that's a fair assessment. Or you're doing software development stuff, running Visual Studio. So a lot of times I recommend technology majors do this type of thing. You can certainly buy a Mac and dual boot both. The disadvantage of that is you got to reboot your whole computer to do anything. But sometimes you just want to test something, or you just need to do something over on the Windows side. So for me, I spend, 99% of the time booted into the Mac OS. But whenever I need to do Visual Studio stuff or something like that, I launch a virtual machine. I have Windows 8 on here. So I launch a virtual machine and run it within the Mac OS to do that type of stuff. And I have enough hardware to support that. When would you want to reboot into Windows? What types of applications? It would be the same applications that are probably going to make your virtual machine really slow. What about games? I always find it funny when you were writing your paper and you looked at Parallels. Parallels out of the two of them is the one that talks most about game support, right? How many of you would ever run your video games in a virtual machine?
I have no other choice.
Yeah, I mean, you wouldn't even consider it, right? So it's kind of funny that they focus on that so much. I suppose maybe like kids games, something like that might be okay, but any sort of real video game is not going to run well in a virtual machine. It's going to maybe show a picture or something like that. So we would typically reboot our Mac into the Windows side to run natively, correct? That way we can have a fighting chance at playing our games. You're going to have hardware support for your graphics card and have a decent enough graphics card, that kind of stuff. But at least you can play your games if you wanted to. Virtual machines, probably not the right solution for games. Now, in comparing those two, most of them have, well, I think both of them at this point, have some sort of feature, VMware and Parallels, that kind of allow it to integrate into, in fact, do I have it right here? Yep, so, I'm using my Mac here, and if I want to launch Internet Explorer, I just click that. I'm not going to do it because I don't know what it'll do to my recording. Because that is going to take up some system resources. But I can just launch it, and it'll launch Internet Explorer as if it's a Mac application. Take a little bit longer to launch because if the virtual machine isn't already booted up, which right now it's not, it has to in the background boot up Windows 8, and then it'll launch Internet Explorer as if it's a Mac application. Well, that's kind of nice. Now it's no different than just using your Mac. And VMware has a similar thing. I think it's called, actually this is VMware. I think it's called Unity. Is that what this one's called? Parallels has its own feature, which I think is even more integrated into the system. I think you can drag Internet Explorer out here onto your bar and really treat it just like it's another Mac application. So they really try to integrate it with the Mac operating system. Now, most of us don't use a virtual machine on a daily basis because it's slow. Because most of what we choose to do with our computers outside of homework is going to be games. Correct? I mean, generally speaking. Most of us, from a using our computer perspective, aren't in a productivity mode because we're not out there working in industry, things like that. So even chances are, if you're out there working in industry, you're not necessarily going to have that virtual machine environment at home. You're going to have that virtual machine environment at the office where you're spending 8 hours a day working on technology stuff. And as a computer scientist, you're going to be working on all sorts of different stuff. For those of you who go into some sort of IT web side of things, if you're the IT guy, but you're also taking on some programming responsibilities, you're probably going to be web programming type stuff, PHP, JavaScript, that kind of crap. And you're going to have to test in multiple browsers. And one of the browsers you're going to have to test in is going to be Internet Explorer, which is actually an interesting thing. How many of you in here use Internet Explorer as your primary browser? None of us, right? What's the most commonly used browser in the world? I don't think so. I think it's still Internet Explorer. I think actually by a lot. So, interesting. Amongst technology folk, Internet Explorer isn't used, correct? But if you're grandma, how do you get to the internet? You double click on the blue E, right? That's the internet. So that's where the internet lives. Blue E being this guy. That's the blue E. So we teach grandma that pick that icon. Grandma goes and clicks on it, and that's the internet. That's the most used browser in the world. So anybody who's writing a website needs to make sure, well, we could say at the very least it looks right in Internet Explorer. But realistically, when you're writing a website, you want to make sure it looks right in the big 3.5, let's say. Internet Explorer, Chrome, Firefox, and then we'll say Safari for the Mac people. I'm really going to say Safari is the half. Because how many of you are Mac users in here? Half of you or so. How many of you use Safari as your primary browser? I do. I use Safari, and if something doesn't work right, I usually launch Chrome. And it's for no reason. It's not like I have some sort of love affair with Safari. It's convenience, I guess. But even among Mac users, we'll just be fair and say a 50-50 split between Safari and something else. Chrome is very popular amongst tech people, right? Firefox used to be that kid, and now people kind of, any of you use Firefox as your main browser? It's not that it's crap, it's just Chrome kind of is the new cool kid. You know what I'm saying? So typically, Chrome or Firefox tends to be everybody's go-to if you're in the technology world, and those are cross-platform. Any of you PC users use Safari? Do they still make a Safari for PC? They did. They also used to have an Internet Explorer for Mac. That lasted a week. It's actually funny. Like why Microsoft would be under the illusion or delusion that Mac users, because a lot of Mac users are Mac users because they hate Microsoft and stuff. Mac users are very culty. I would say technologist-based Mac users, like us, we're probably less culty. We're using it as a purpose. I push Mac in computer science because it's it's two machines for the price of what I would say 1.7 or something like that. So it's the right tool for the job for us. But when you go into the Apple store, you're kind of looking where the Kool-Aid is. I mean, it feels kind of like culty in there, right? I mean, it's, I don't know, you kind of feel uncomfortable. Like if they had free Kool-Aid in the Apple Store, would you drink it? Because you go to Bayshore, right across the little street there, they have that Teavana. They're giving out free tea. You'll go and try their tea. It's like, oh, it's a tea place. I'll drink their tea. But what if Apple was giving out Kool-Aid or even water? If it's bottled water and it's still sealed, I'll drink it. Anything else, I'd say I'm out. So, how did we get off on that tangent? Oh, the browsers. So in any case, running a virtual machine in a productivity environment gives us the advantage of running lightweight applications. Internet Explorer is a lightweight application, right? Most of the slowdown you're going to experience in your computer is from having the virtual machine launched. So if we need to test something in Internet Explorer, we'll launch Internet Explorer. Probably then, I think we can suspend the, we can shut it down or whatever. I don't even have it started right now. But we can only have it open, only have it taking up our system resources while we're testing something. If we're running Visual Studio primarily, if we're doing a bunch of .NET development or something like that, you may launch that in a virtual machine, or you might choose to reboot into Windows. If you're primarily writing, if you're going to spend the next 3 weeks of your life writing Visual Studio code, writing .NET, C# stuff, whatever, chances are you're probably going to reboot into Windows and run that natively rather than run it through a virtual machine. Because you're not going to be testing .NET stuff on the Mac side, unless it was web-based. But even then, you're probably not going to be testing it too much on the Mac side until you're farther down the line. So you'll reboot. So it's the right tool for the job. So at the end of the day, we could probably say that VMware, their product line is more of an enterprise product, where Parallels, their product line is more of a consumer product. But maybe it's choose the one that was on sale. Something like that.
Never on sale. Parallels is never on sale.
I don't think that's true.
Really?
Almost all of them are always running some sort of upgrade sale or something like that. I was a little, is it miffed? What's the right word? Pissed. I was a little pissed that as soon as Yosemite, as soon as Yosemite hit, all of a sudden I had to buy a new license for my virtual machines for them to work. What kind of racket are these guys running? Okay, so virtual machines, certainly good for a lot of reasons, but not the right tool for every job. Punchline here being, use the right tool for the job. All right, so now we get into another kind of virtual machine, something that we're all familiar with at least at a high level. That's the Java virtual machine. Well, historically, we've talked about the good and the bad of the Java virtual machine. Java virtual machine, the advantage it gives us is allows us to run our Java programs on multiple platforms. Any platform that supports the Java virtual machine. Java virtual machine being a computer virtualized on another platform, running as an application. Now, the Java virtual machine isn't as slow as running, virtualizing a full version of Windows or virtualizing a full version of Linux, but it's still slower than running something natively. The Java virtual machine is only virtualizing an environment that allows you to run a Java program. That's the only thing that it's virtualizing. The bare minimum, let's say, for running a Java program. That's going to be all the different things to interact with the operating system for network stuff, for the windowing environment, that kind of stuff. Not the ability to launch a bunch of applications and multitask and memory manage and all this other stuff. So only certain aspects of the virtual machine for Java act as a general purpose virtual machine. So we can really look at the Java virtual machine as being a domain specific virtual machine as opposed to a general purpose virtual machine like our full operating systems. Slow, but not as slow. Okay, So, Java Virtual Machine, is it good? Yeah, it's good for programs where Java makes the most sense. But the virtual machine aspect of it is still what we have to make that choice. As developers, we're going to choose, does this application need to run really, really, really fast? If the answer to that is yes or even close to yes, we're probably not going to choose Java. If the more important route is that this application needs to run on multiple platforms, needs to run on Windows, needs to run on Mac, needs to run on Linux, needs to run on whatever, OpenBSD, one of the Unix flavors, then we probably write it in Java, so we only have to write it once. It's an advantage. Okay? So we see how this guy works. We have we compile our program. It compiles it down to a .class file, which is Java bytecode, right? Java bytecode being a low-level language that is understood by the Java virtual machine. Then we have the Java interpreter. Remember when we talked about programming languages? We have, there are two kinds of programming languages, compiled languages and interpreted languages. Java's kind of both. So Java compiles down to Java bytecode. Then during runtime, it gets interpreted. It gets interpreted into the low-level language of the host system, Windows, Linux, whatever. Okay, so Java Virtual Machine fills a role, has a role, but it's not the right tool for every job. Make sense? All right, this is probably going to be a wasted. Oh, I like this one, though. Debugging is twice as hard as writing the code in the first place. Therefore, if you write the code as cleverly as possible, you are, by definition, not smart enough to debug it. That's a good one. But there's a lot of truth to this. For those of you who, at our level now, some of you are probably pretty competent at programming, but some of you still struggle with it. Something you probably recognize is it's easy for you to get a program that runs. It's difficult to get a program that runs right. You run into all sorts of little bugs and things like that, and it's difficult to debug them. That's the hard skill set with programming, is debugging your own code. So I'll throw this out there. Again, I throw it out in most of my classes. If you are fixing your code by guessing, just changing crap and trying it, probably not going to do yourself a very good service long term. You would be making changes out of logic. Okay, well, I'm just going to say this is a wasted slide. This is just going through debugging algorithm stuff. Here's the program called dtrace for Solaris, which nobody uses anymore. Talked about the bootstrap. Stupid. System boot. Ha! Good. All right. Relax. Let's see if we're on to good stuff now. Oh, I don't want to launch PowerPoint. Die. See, real Mac users, they launch PowerPoint things in Keynote. Let's just say, any of you have Microsoft Office on your Mac? Do you use it? Really? It takes forever to launch.
I don't disagree with you.
Well, how could you? I'm right. All right. Oh, we're on to real stuff. Good. All right. So, let's talk about processes. What?
I was wondering why there were dinosaurs.
Oh, it's actually a famous thing. Yeah, the book we use in here is a book by these guys called Silverschatz and Galvin. It's the famous dinosaur book for operating systems.
Oh.
But every single year they come out with a new one at the price of $150. So I just use their slide set and don't require the book. I make them pay me half of the $150. Everybody's got a good deal, right? So you guys each wrote me a check for $75. Oh, missed. But that's what the dinosaurs are about. Yeah, it's Yeah, see? Silver Shats. I like that name. I could have used some of that this weekend. Your minds. Your
Where are you
mind.
going after the rotating shaft?
That's not even this class.
Doesn't matter.
Rotating shaft was architecture. Okay, so we're going to talk about processes. We've talked about these at the high level. Now we're going to get into the details of process management. So concept of process, process scheduling, operations on processes, inter-process communication. We're going to spend quite a bit of time on that. That's when we're going to start writing some code in here. We're going to have multiple processes. We'll spawn them as we might even do some forks. Abe, we might fork some children. Just so we can explore some of the inter-process communication of having the children talk to each other after they've been forked. We'll also deal with threads. So kind of looking at the difference of inter-process communication when we were dealing with separate processes versus multi-threads, where threads have to just talk to each other or talk to the parent that spawned them. So there's all sorts of ways that we need to deal with inter-process communication that are very important, really as important today as ever, especially as we start dealing with multiple CPU machines, multiple core machines, where not all tasks can take advantage of the multiple cores. So when somebody writes a piece of software, if they wanted to be able to leverage multiple cores, they have to write it intelligently so it can do that. Well, so some tasks might not double in speed with 2 cores. Maybe they get 1.3 times the speed with 2 cores. But certain aspects of that application have to wait on other aspects of that application to finish, because things have to happen in a certain order for many tasks, right? So we need to have the ability for those threads or those processes to make other threads or processes aware that they finished their part so they can pick up. Go ahead.
Say you write a program that was designed to have more than 2 cores, say 4 cores, and that will work best on 4 cores. What happens if you have 2 cores? Is it just...
I would say that what you just said, it's not that it doesn't exist. There's probably some very, very specific applications that somebody might write something that would be most beneficial on 4 cores. But generally, somebody's going to write an application that is either linear in nature, 1 core only, or is nonlinear in nature, where it relies on the operating system to manage the cores, whether it's being done on 2 cores or 5 cores or whatever, however many cores there are. It's either 1 core or multiple cores for most applications. So it's that choice of, do I need to allow my processes to communicate with other processes and let them know when I finish something? Think of this like a, what's the race where you hand off the baton? Relay, right? The person who's running second can't take off until you hand them the baton, until you let them know it's their turn, right? Because it's against the rules. In a program, it might be that they can't start their process. They can't start doing their thing until the previous guy has produced what they were supposed to produce. So we need to let them know that that's occurred. So inter-process communication allows us to support the order in which things will happen. The operating system itself will manage which CPU is going to run that particular process and when. Something like that. So a process wouldn't get into the ready queue, wouldn't start waiting to get CPU time until it had been notified that I can start doing my thing. I'm trying to think if there's some specific applications that would work with what you were asking. I can't come up with one off the top of my head, but it probably exists. Probably some sort of simulation or something like that was written very specifically for a piece of hardware that had 4 or 6 processors or something like that.
Well, that would probably work on something less, just not as efficiently.
Probably, but my guess is if they were writing it for, it would be really proprietary software, something that was written specifically to work on something. Maybe even a good example would be PS3. PS3 games. When the PS3 came out, the Xbox 360 had a 3-core processor. The PS3 had an 8-core processor, kind of a special processor. I can see, and I don't know this for a fact, but it's certainly plausible that the game makers who were writing at least the PS3 native games, the ones that were, only on that platform, that they wrote those in terms of those 8 cores because they knew that was the hardware it was going to run on. So it's possible they were able to make some decisions that specifically took advantage of those 8 cores, where running on less or more cores would have been problematic. I'm guessing, but that might be the closest example I can give you right now. So interprocess communication, examples of interprocess communication is IPC, is interprocess communication, and then client-server stuff. Skip that. All right, so process concept. Just a quick review. So we can execute. This first thing is more of an operating system difference. So we have some operating systems that are batch systems where you just have a big list of jobs and just work through them. Then we have a time-shared system, which is going to be user programs or tasks. So this gets down to the thing we talked about right before the midterm about goals of different operating systems. Some operating systems have a goal of just getting things done. Other operating systems might have a goal of making end users happy, multiple end users happy. Okay? So when we deal with time-shared systems, that could be making a single end user happy or multiple end users happy. But the point is we're not going to just have a list of 30 jobs and we're going to finish the first one, then go on to the second. Finish the second, go on to the third. We're basically working on all 30 at the same time, giving each one a little share of the CPU time. Okay? So a couple of different mentalities of process management here. So this particular book uses the term job and process interchangeably. So when we call something a job, typically that's something that's running on the CPU. A process is something that exists that can run on the CPU, but they're relatively interchangeable. Process is a program in execution. Process execution must progress in sequential fashion. That kind of indicates that I told you this backwards. That a process is running, a job just exists and is capable of running. Doesn't matter. So, what's inside of a process? What are the components of a process? At a high level, a process is going to have a program counter. That is, which line of the low-level language is the current one to be executed. So, when we think about one of our programs, we're going to compile it. So, it's going to go from our high-level language down to a low-level language. That low-level language is going to be a set of instructions that have a one-to-one relationship with the magic tricks that the CPU knows how to do. Right? So within a process, we're going to have a program counter that's going to tell us which of those instructions comes next. And we need to have that specifically to support this idea of processes leaving the CPU and coming back later. So we know where to pick up where we left off. That make sense? So we got to know which line of code we're on. Every process will have its own stack. Okay, we have the stack data structure, which is a last in, first out queue, like a stack of magazines. And we use stacks to hold things and pop them back off. So we push something onto the stack to use again in a minute, pop it back off. So each process has its own copy of a stack. We also have an operating system-wide system stack that could be used as well. We've seen this per process stack before in Java, where we write a infinite recursion, and we get the stack overflow or stack whatever it is. This guy. Stack Overflow error, where we run out of crap, run out of space on our stack. Okay, so each time that we called this die method again, we pushed the previous version onto the stack so we can come back to it later. So we can execute a new copy of it. And eventually we ran out of space in our stack because we just kept pushing it onto the stack because we have no logic in here. What does die do? It just makes a copy of itself and pushes it onto the stack. The whole purpose of that method is to overflow the stack. Java protects us from that. If we had written that in an old C, in a C language, using an older runtime, I think our modern runtimes would actually catch this. We could potentially crash our computer, run out of memory in your system by just filling up the system stack over and over and over again. So we've seen an evolution of processes where each individual process has its own stack. So the worst that could happen is a program crashes rather than the operating system crash. Make sense? So kind of a evolution of operating systems. And then every process has a data section, a collection of variables for holding its crap. Within this data section, this is kind of a catch-all for a bunch of stuff. This needs to support our concept of context switching. So when we leave the CPU to come back later, the program counter tells us where to pick up. Where we need to start again next time. But this data section is going to hold the state of all those variables, including the registers and stuff on the CPU, so that it can reload those next time it comes back onto the CPU so it can legitimately pick up where it left off. We can't just start at the next line of code that we're supposed to start at. We also need to put everything back into its place on the CPU so that we're picking up exactly where we left off. So this data section can mean a lot of different things, depending on the process. Okay, so process, multiple parts. We have the program code. This is the actual text of our code, text of our program, in the low-level language. Okay? So a process doesn't exist at its high level. You won't look at it. If you were to look at the insides of a process, you wouldn't see Java code or C# code. You would see assembly code, low-level language. Okay? So current activity, including program counter, the processor registers, so a copy of all the stuff that's currently happening on the process on the CPU. We'll have a stack containing temporary data. So this is function parameters, return addresses, local variables. So just like we showed here. This guy had no parameters, but if we were to put in a parameter, each time we push one of these onto the stack, we'll put in the name of the method, the memory address associated with this particular call to the method, all the parameters and the values associated with them for that method. So all this crap gets kind of packaged up and thrown onto the stack. All right, so it's not just a single number or something like that on the stack. All right, data section containing global variables. So these are variables that are software-based variables associated with the entire process. A heap containing memory dynamically allocated during runtime. So heap is actually another data structure. I sometimes get to it in CSC300, sometimes I don't. Do you guys know what a heap is? All idiots. All right, so a heap. Remember we talked about queues, right? Queue is a first in, first out, like a line. Go to McDonald's, that's a line. A heap is another name for a heap would be a priority queue. So we kind of talked about it probably in 300 at least a very, very, very high level. I probably use some sort of example of if you're at McDonald's and the president walks in, chances are he's not waiting in line. Different people in line may have a higher priority than others. Okay, so a heap is a priority queue where it is in general first in, first out. But some members of the queue may have a higher priority and can cut in line. Okay, so that's what a heap is in general. We'll talk, I'm sure, more about how the heap is actually used with the process later. A program is a passive entity. Processes are active. So that is, a program lives on the hard drive. It sits there. When we double click on it and it gets loaded in memory, at that point it's become a process. Okay, and now it's active. It's in motion. Program becomes process when executable file loaded into memory. Process when that's not even good English, right? Program becomes process when executable file loaded into memory. Did you write this? Yeah. And I know my English. I don't. I know. I don't want to write that. But I think he's right. Program becomes a process when executable file is loaded into memory, right? Program becomes a process. Oh, when an executable, yeah.
Oh, you don't hack that, but otherwise program is the same type of amount, like it's almost like a proper amount.
So double click KK thanks. All right. Execution of a program started via GUI, mouse clicks, command line entry of its name, etc. Whatever. So this is the equivalent of double clicking. So we can double click on it, we can launch it from the command line, whatever. That's when a program becomes a process. Or in modern day, it might become multiple processes, depending on how many times we fork a.
More the better.
Yeah, so we have a. What? Tim, are you paying attention?
Of course.
He's supposed to be shadowing you, and you're just teaching him to not pay attention in class. Seriously. The joke we keep making is we have an operating system term called forking, F-O-R-K-I-N-G, and it's when one process gets split into two processes. But these young minds out here keep misinterpreting the word.
Oh, you have to spell it.
I have to make sure that I'm enunciating. This is all recorded. If like the dean gets a hold of this or something like that, this is all classroom appropriate stuff with devious minds interpreting it. That's right. He said it, so I get it.
Yeah.
Point. Seriously, so good. I'm always like one line ahead of this thing. So one program can be several processes. So when we double click on it, it might spawn off multiple processes or multiple threads is the more modern way of doing it. But that doesn't mean that modern day programs don't also have multiple processes. They might have multiple processes, and each of those processes might have multiple threads associated with them. So it really is the right tool for the job again. So again, I don't want us to think about this concept of forking as being the old way of doing it. And the modern way of doing it is multi-thread. Each one kind of has its pros and cons. So you want to choose the right tool for the job. This is only one example of when a program might have multiple processes. So if you are on a multi-user system and you have, let's just say 30 users using the system at the same time, and they're all going to run the same text editor or something like that. Each time, each user that launches that text editor, that program would become a process with its own process ID owned by that particular user. So that program would exist in memory multiple times and have multiple processes. That would be one example. Another example is we can launch a program. I'm speculating here, but I think it's a pretty good speculation. If you launch Photoshop, which is a pretty beefy program, right? If you launch Photoshop, I would speculate that Photoshop probably instantaneously creates several separate processes dealing with some of the major aspects of the application. And then each of those processes may also then spawn off multiple threads. But that would be an example of one user launching one program and that program having multiple processes being created. Make sense? So, right tool for the job is the punchline there. So, process in memory. So this is what it looks like, a process in memory. So we're going to have our text, we're going to have our data, we're going to have our heap, we're going to have our stack. And the heap and the stack kind of share the same global memory space. These aren't the same data structure. They'll be separate data structures, but there's like a chunk of memory associated for data structure crap with a process. And these two guys kind of share it. All right? So this would be a picture of what one of those guys looks like in memory. So, process state. At any point in time, a process has a, what am I currently doing? So, a process executes, it changes state. So, a process is considered to be new when it's just being created. It's considered to be running when it's actually running on the CPU. It's being executed. It's waiting when the process is waiting for some event to occur. That could be an interrupt, when it leaves the CPU to go and wait on I/O. Remember that we talked about that, the high level? It could also be that it's run out of time on the CPU and now it's gone back in line. But it would only be, in that particular case, it would only be waiting for a second. Let me just finish this slide real quick and then we'll call it quits. So that's when it's waiting. Ready means I'm not dealing with I/O, I'm ready to get CPU time, I'm standing in line for the CPU. Okay, so the process is waiting to be assigned to the processor. Terminated, process is finished, we've hit the X to close it, whatever, it's done doing its thing. So that process is terminated and will eventually be cleaned up by the system. Okay, so a process has a state associated with it. Make sense? So we'll pick up here next time, which is just a review of what we just did, but we'll talk about I/O event type stuff. But and I will try to get your papers graded tonight. Now that I'm kind of back in the game, I'll try to catch up on everything. All right, I'll see everybody on Wednesday.